can we, and also Igor set the stage for walking into technical issues. So, can you guys hear me? All right, so I'm gonna first say thank you to everybody here. My first thought in seeing some of you guys was everybody looks a little bit older, but then I realized so do I. Okay, so it's really nice to see you guys all in the same place, and so I'm going to talk a little bit about some new work in my group, which is actually currently unpublished, more because this is the right audience for feedback and references. So this is an open discussion in some ways. I want to start by saying this is 35 years, but I want to start by saying a few things about how ITAMP has. Thank you. Where did you get the cup? Okay, I don't know whose cup this is. I just want to start by saying a few words about how my journey at ITAMP started. I was in the first winter school in Arizona at the ITAMP Winter School. It's because we were in Arizona and our advisor, Pierre Maestre, volunteered us to go to this winter school where I met many of you guys, the senior folks, for the first time. And this was the group of lecturers, and it was very inspiring. And I made the mistake of telling my advisor that I found one of them a little intimidating. And he was just like, "What? I'm very offended that you don't find me intimidating." And then he told this to Roy Glauber, who was one of the lecturers. And this was a very long winter school, and they both pretended to act offended that I wasn't intimidated by them. And long before this winter school ended, I made this executive decision that I'll never be intimidated by anybody, because I just had this mental image of these two people who are great scientists but not great actors, acting all offended, that I don't find them intimidating enough. And that really helped. When I got to ITAMP, I got to interact with a lot of senior people, just ask questions, whatever was on my mind, and one of them was Alan Aspe, whom I asked a lot of quantum optics questions. And one of the biggest things he taught me was always encouraging me to just think outside the box and keep pushing it. So it's nice to see work with Igor, see the light of day, and more, kind of go into very interesting directions, and also the similarities between what we're thinking of these days. So that's really nice. I had a lot of great mentors and peers at ITAMP, and a lot of you. I've asked a lot of science questions, but also I've learned a lot about how to do science, and I think all of you guys know the kind of questions I've asked you. You're such an inspiration. I'm like turning my hairstyle into yours. All right, so I run a small quantum optics theory group at the University of Delaware, mostly led by brave students, and I kind of oscillate between what are the smallest force, acceleration, displacement, you name it, you can measure, why, how to do better. And then I go into these philosophical spirals of why should I bother with all of this. And so a lot of recent work has been more about gravitational wave sensing that Igor mentioned, and more recently dark matter and dark energy sensing using quantum optics style systems. And when I think about what led me to think along these lines, a lot of it has to do with this place, the Center for Astrophysics, which has been around for hundreds of years. And some things haven't changed since 1855 and what you see outside right now. And one of the things is when you walk outside that door, there's a sign of Harvard plate stacks. And that's 500,000 photographic plates that were analyzed to show a lot of the stars, and a lot of very seminal work was done here, including some by Henrietta Swan Leavitt, who lived on Linnaean Street, which is on your way to my previous apartment, or Simon's Coffee Shop. And then I would think about this was the first standard candles, essentially. And then Cecile Payne-Gaposchkin kind of challenged the box in many ways by saying stars are actually made of helium and hydrogen and not the things that Earth is made of. And she looked at those photographic plates that are finally being digitized, all like hundreds of years of that data. And then two dudes sat down in Perkins right over there and formed the High-Z team, which showed that the universe is accelerating, which was another like very out-of-the-box thinking. And so there's a lot of out-of-the-box thinking that has been going on like outside the ITAMP bubble at CFA. And it's actually very, very inspiring to be here in this ecosystem and think about all the great things that have been done here. And so I'm going to give you a little bit of the AMO Girls Guide to everything in the universe. Essentially, atomic physics, definitely not atomic physics. That's all there is to know. So more than 95% of our universe is technically not atomic physics. This is dark matter and dark energy, and we don't know what it is. And everything we know about these, in many ways, can be summed down in this slide and the slide afterwards. And so about 23% of our universe's energy budget is dark matter, which is most of the mass in pretty much every galaxy that we know of. And the only thing we know is that it interacts gravitationally with standard model like normal matter. And the estimated energy density that we think in our solar system due to dark matter is about 0.3 GeV per centimeter cube, which is an estimate we came up with by looking at rotational dynamics of several galaxies, and has the resolution of about a parsec. So this number, so you really don't know if there is any dark matter like in every centimeter cube. So this number is kind of iffy, which is why we don't know how this dark matter is clumped. It could be the right sprinkle of black holes or some ether-like thing kind of permeating Earth and everywhere else. And everything I'm going to talk about goes in this category of the last 20 or so orders of magnitude, and the mass of dark matter particles, so 1 eV per c square is 10 minus 33 kilograms, so that's here. And so you're looking at things well below, which also means that you cannot look for gravitational signatures. So it's interaction with normal matter, because one particle is like 10 minus 30 something, or minus 22. Of that. So about dark energy, which is an even bigger problem, and particularly because of this place's role in coming up with this stuff. So I've always found it very inspiring to kind of think about this from a quantum optics perspective. It's most of our universe, over 72% of the universe. There is absolutely no theoretical framework. I think this is the 25th or 26th year of clear demonstration of accelerated expansion of the universe, and there is no place to start with a theory of that. And if you just think about this as some sort of a 0-point energy, and you add up like all the field modes you can think about in the universe, you get an answer which is 120 orders of magnitude bigger than what is consistent with the observed value. So the point is there's room for a lot of theoretical ideas. It's always an opportunity. So how do we know about whatever the numbers that I showed you? This is a picture of Hossein at a telescope that I grabbed from the ITAMP website. Everything we know because of looking outside. So with more telescopes and better telescopes and more data analysis techniques, we should be able to kind of constrain dark matter and dark energy a bit better. And then in terms of direct detection, so how do I know I've seen dark matter particle or something? There's a range of experiments that are well established and some underway. And there's a lot of AMO experiments that are coming up that are about more like tabletop experiments that are essentially precision measurement experiments that are also looking for dark matter. Now, in my group's recent efforts in the past 5 years or so, I've been a student of astronomy, kind of learning things. and writing papers about like how to do this kind of stuff. My PhD was in optomechanics, so it was kind of nice to take some of those old optomechanical systems and ask the question from what is the smallest force or displacement you can measure to what is, can you constrain some effects because of normal matter and dark matter coupling. And we did some work in that using mechanical systems and later using fibers. Most of it was led by my student Jack Manley. I learned a lot of cosmology and astrophysics from Daniel Grin, and I collaborated with Dal Wilson. The superfluid helium Weber bar is now also a dark matter detector. And it's being led by John Davis's group in Alberta. We had some margaritas and decided on the name Helios. Richard and I have this margarita cancellation club where we always say like we'll have a margarita to celebrate something and then we never do and we cancel each other's margaritas. And so if we actually have margaritas, we need to. I know, it's been 10 years of margarita cancellations. Anyway, we should have margaritas so we come up with like acronyms and stuff. And Jack Sankey's group is involved. And then there's some like indirect detection experiments involving dark energy, mostly because just like spending time here, I've always been fascinated by dark energy, and this was a lot of learning nonlinear optics, cosmology, astro, and whatnot, and throwing students at that, and just a lot of fun. So I'll talk a little bit about how I think about ultralight dark matter as a quantum optics person, and then using some old school, like really old school, long before my time and your time, quantum optics to characterize the state of dark matter, and a little bit more about how we can think about dark matter as an open quantum systems problem. And so this is why I'm here to kind of get feedback from all of you guys. And so when I was doing some work on vector dark matter, people always started people always refer to that specific type of dark matter as dark photons. And that name kind of stuck, and this analogy works for a whole bunch of beyond standard model fields. You can kind of look at these fields like dark matter or dark energy, things, bosonic fields we have not seen, and kind of step back and think, what is the bosonic field that I have a feel for? That's photons, right? So what if you were blind and I told you there is a fancy particle called a photon? How would you convince yourself that there is a particle called a photon? Because you can't see it because you were blind, right? And so this is, well, there are two ways. One is what Igor was talking about, photoelectric effect. They act as real particles, do something measurable. I look at the signal, I go like, oh, there was a photon. And that's a clear direct detection experiment. Another one is a Coulomb's law experiment. So we know here photons act as virtual particles. They mediate forces. So if you see two balls, attracting, repelling each other, you can kind of say there was this mediator particle. And that's why I can convince myself that there were photons. So this is more of an indirect detection of photons, because you can do the Coulomb's law experiment in pitch dark and you would get the same answer. So it doesn't matter how many photons are actually there, but you will get the same answer. You can still prove there is that thing called a photon. So this is kind of what is done in dark matter experiments. So pretty much every search you can think about is an example of a direct detection search. So these are ADMX or Super CDMX or Helios or every AMO experiment. You can also have these fifth force-like experiments, which are these EP violation experiments or things of that nature where you're looking at weak forces and you kind of constrain the mediator. And so that would be an example of these things. When it comes to dark energy, we don't hear of any direct detection experiments because, and I know, so people who care, there was the energy density, I should say this, so I skimmed over this, but there's about 0.3 GeV per centimeter cube of dark matter where we are, and there's about 4 keV per centimeter cube of dark energy everywhere in the universe, so there's 5 orders of magnitude between them. There's a lot less dark energy than dark matter, and it's very hard to set an experiment to do a direct detection. But it would still mediate forces, and that's the flavor of dark energy, like particle physicsy experiments that you can think about. So if there's a tabletop experiment for dark energy, it's this. So going back to dark matter, the estimated energy is 0.3 GeV, and we don't know how it's distributed. So if it's the right sprinkle of black holes, our only hope is gravitational wave detection. If you have like clumpy object-like things, so if I take 0.3 GeV per centimeter cube and multiply it by the volume of the Earth, I get about 100 grams. And 100 grams of dark matter, like clumped in a tiny rock, is totally detectable using its gravitational coupling. But it's a very rare event. What are the chances it's right on top of your kitchen scale, right? But it'll be a recoil detector. If it's sprinkled a lot more, it's going to be a single phonon detector that's going to give you the answer. And if it's more of like an ether-like thing, you essentially have to build an amplifier, and that signal would be there at all times. It wouldn't be raining dark matter. You'll be sitting in a sea of it. And so most AMO quantum optics experiments that are in this regime are in this amplifier of a continuous signal. And a model that's especially coming from AMO you can think about is essentially you're swimming in a galactic scale Bose condensate or variation thereof. And one can ask, how do you know that you are swimming in a galactic scale BEC? We don't know. And so this is something I learned a lot from your papers, Andre. And actually, you sowed the seeds while I was here. For very light dark matter, think about them as bosons. Think about them not as a particle kind of raining dark matter, but you swimming in it, so more of a wave that you're in. The amplitude of this wave is proportional to how much dark matter there is. The frequency is related to the mass of dark matter, which we don't know, to many orders of magnitude. And essentially, this is like a Maxwell-Boltzmann-like distribution. There will be some Doppler shifts in frequency because, it's a Maxwell-Boltzmann-like distribution that you're dealing with, which gives you coherence time. No matter what the frequency, you essentially have something like a cosine for a million oscillations. And then there's a phase flip. Okay, so this is a review of Andre's paper, and then I started to think more about, so essentially what you have is a multi-mode bosonic field, which with a very large average occupation number, and so there must be a density matrix associated with it. And what kind of astrophysics or cosmology or quantum optics can you kind of gather from a quantum field like this? If you look at the diagonal elements, that's going to tell you about your various velocity components of your dark matter. And there's a lot of astrophysics there because so we are at the spiral end of the galaxy, and before the last time we were here, another galaxy merged into us, which probably had its own dark matter, so it hasn't quite thermalized, and how much dark matter it is and where it's coming from. All these things are deviations from essentially a thermal state. And so one can tell about the galactic scale, like mergers and acquisition history, by looking at the diagonal elements of this density matrix. And then the off-diagonal elements of the density matrix essentially will tell you about coherence properties of this quantum field, and has it stayed quantum over cosmic time, or has it decohered? We don't know because we haven't seen it. So a lot of particle physics people is like, why do you want to think about axions or any ultralight dark matter as a quantum field? Because at like micro EV or so, you have about 10 to the 30 particles in this field. So coming from this is something Igor was also talking about, that Wigner function is not negative. You're not doing a take a quanta, give a quanta kind of changing, and it's going to be very hard to observe single quanta effects. This is the same problem with gravitons, right? Like, how do you observe single quanta effects if you have 10 to the 36 particles? And this is a very old problem in quantum optics. In fact, this is the birth of quantum optics. Before Einstein, there was Planck, who explained sunlight by quantizing light, right? So we had to quantize light to explain the solar spectrum. And so depending on how you, and like, which is a very large average occupation number multi-mode bosonic field. So one needs quantum optics not just for Fock states, but to explain a whole bunch of other things. In fact, to distinguish like thermal states from lasers, these are all high average number multi-mode bosonic fields, but from a quantum optics standpoint, they are all very different from each other. And this kind of, and this was something that was very beautifully answered in Roy Glauber's paper, Quantum Theory of Optical Coherence, and it's been a joy to kind of apply it to ultralight dark matter and discern like what kind of astrophysics or cosmology I can get out of this. So one can assume you have a thermal state, density matrix, just whatever quantum correlations were there are gone. And then ask ourselves, like, take different models of the velocity distribution of dark matter in our galaxies that are, that come about from various, well, depending on who you ask, various, so standard halo model is essentially the Maxwell-Boltzmann distribution of dark matter, and then there are corrections to it depending on which galaxy merged into us when, and how much of that dark matter is now our dark matter. And all of this would show up in the bunching statistics. So the Hanbury-Brown-Chiss experiment, which showed this bunching in the second order coherence, so the intensity correlations, if done with dark matter, so you need a particle detector, would show deviations from the standard halo model of the mergers and acquisitions of our galaxy. On the other hand, and this was done for laser and then later for ultra-cold atoms, if you see a G2 of 1, then you have a nice coherent state. So if you indeed are swimming in a galactic scale BEC, you build two detectors, look at the intensity correlations between them, and one should get something that's close to a 1. And as was also seen in ultra-cold atoms, it was never 1, it was a little bit bumpier than 1 because it's always a statistical mixture with a small thermal component. So deviations, and one would expect something like that if we ever see dark matter, because seeing dark matter means it's interacting with something. And if it is interacting with something, then it has been slowly decohering over cosmic time, which means it's probably no longer in this coherent state. It has been slowly thermalizing with the rest of the universe, so one expects something in the middle for all of these. So deviations from bunching statistics and stuff would tell us about the quantum coherence of these effects. And then, so this is about characterizing the field, and one can go back to this and look at, like, how do I detect it? How do I model the detector talking to a lot of dark matter? And when we started working, and one of the reasons, or at least like for me, was I don't know how to think about things in terms of Lagrangian densities, and I wanted to just look at the Hamiltonian and see what kind of what ways to kind of do very precise measurements, so go beyond the standard quantum limit. So once you have the Hamiltonian, one can design, what is a non-commuting variable, do a Q&D measurement, all that stuff. And people have been thinking about it for dark matter. When we started, I couldn't find the Hamiltonian for one of the most popular dark matter candidates, QCD Axion. So we derived it, and when you look at it, it looks essentially, and it is, you have a single mode harmonic oscillator, which could be your haloscope, or depending on your detector, interacting with a multi-mode field. And one can start to apply this like master equation like approach to these problems, and write down the density matrix. You essentially can think about whatever your detector is, hopefully a quantum system because they are more interesting. They're sitting in a bath of dark matter. And it's not just a bath, it's a very hot bath of lots and lots of particles, and that is what dark matter is. It's your and you are very weakly interacting with it because we haven't seen dark matter. And there is a lot of it, and the state of dark matter is not changing because because of the interaction of your detector. So this is like it checks off all the open quantum systems. Let me write down the Lindblad equation approximations. And when you do that, you can start to think about different types of detection methodologies in the framework of quantum jumps, and a lot of like interesting intuition starts to come about, which I don't have time to get into. But essentially, once this is when my students were like, oh my God, this is like a very hot thermal bath. And that's what it is, except it's not thermal, which is what I was talking about. Like it doesn't have to be a thermal state. In fact, there is a frequency spectrum associated with it. And if you have a frequency spectrum, you can't assume Markovian kind of statistics, right? You have a colored bath. And also there's like a whole bunch of debate about whether it is a BC or a thermal state or a squeeze state or whatever. And one way to just not walk into and like people feel very passionately about the state of dark matter, and we haven't seen it, so everybody's allowed to their passionate favorite density matrices, which is why I was like, oh, we'll just solve the problem in Heisenberg-Langevin basis. So if you solve the Heisenberg equations of motions, there's a couple of things. It helps us, actually we were stuck there for quite some time, and then we realized you can model a colored bath just like another cavity that you're coupled to, which has a line width that is of this order of the line width of your dark matter bath. So this kind of sidesteps, it gives us a way to kind of look at the interaction with the detector and be able to solve for some things analytically. You find that the noise or the coherence properties of your dark matter bath would manifest themselves if you're looking at the G2 function of your cavity. And there's a whole bunch of other fun stuff that you can do, but essentially one can start to go into this to have a better sense of how to come up with a detection setup, because this is a very different type of an open quantum system problem. Here we have a quantum system very weakly coupled to a bath, and what we're trying to do is find out about the bath. So how do you learn about the bath? How do we optimize the system to learn about the bath? That's the quantum optics version of the dark matter detection problem. And it turns out there's quite a few things, as I talked about. So, and this is something Igor brought up, like Willis Lamb's ideas, and there are a lot of, so this whole thing has gotten me thinking about what is a photon and all those things. And actually last week or 2 weeks ago, I came across this paper and I found this quote from Roy Glauber that effectively a photon is what a photodetector detects, and just forget about the rest, because you can really think a lot about what is a photon, and you wouldn't be alone. Many people have been thinking about it for 100 years. Willis Lamb made sure not everybody could. There was a certificate you had to have to use the word photon. And so I'm going to add to it that a dark matter particle would be whatever a dark matter detector is going to detect. Right? I'm a theorist here. So whoever finds it, good for you. That's what dark matter would be. And maybe it's not an ultralight field. Maybe you're not sitting in a bath of dark matter. It was a sprinkle of black holes or whatever it was. But I got to learn a lot of quantum optics. I'm happy with it. And but the other thing is you don't know unless you don't see it. Right? So we should still be looking for or like designing a whole bunch of experiments, including atomic systems, even though one could argue that, it might not be the one that detects it. Because even if you don't find it, and this was also the case with light, the Michelson-Morley experiment was looking for this ether being dragged as Earth goes around, and that the theoretical curve was this, and the experimental result was that flat line, and they didn't find what they were looking for, and because they didn't find what they were looking for, we have a much richer theory of light. And we think a lot about what is a photon, 100 years later. So constraining the available parameter space for dark matter and dark energy and other bosonic fields would hopefully lead to a better understanding of their properties and their interaction with the rest of the universe. And with these thoughts, I just want to, I have no idea how far over time I am. Okay, well, so, so I just want to acknowledge fruitful discussions with the people here and a lot more people somewhere in the room. And this was the work of 3 of my students. And I'm happy to take questions. Thank you.
Questions? Andre first. Ask my
Thanks for the talk. And I'm just curious, how do you compute all the diagonal matrix elements of the density matrix? Because diagonal matrix elements. The question is about off-diagonal matrix elements.
I don't compute them. I assume it's a coherent state. Yeah. So, okay, Richard.
So I don't know anything about this. So
neither do I, or anybody else.
So my question is, if I have, so you assume very light bosonic dark matter,
Yeah.
so the critical temperatures were very large because of that, I guess, and thereby in the microwave background, they are still a Bose-Einstein condensate. And if you have a flat distribution, it means non-interacting. What prevents them from collapsing? Because there's still gravitational interaction, and if G1, G2
that's
would
a very good question. This is why people don't say it's a Bose condensate, because the only interactions we know of are gravitational, which are attractive, and so you cannot have a Bose condensate with just attractive interactions. You will have to invoke other so-called miracles of particle physics to have a condensate dark matter. But my hope here was that, it doesn't matter. How would you characterize if it is a condensate?
So basically your results would be universal a little bit with respect to the state in which the matter is.
Yeah,
okay.
so this is like a limiting case.
Good. That
so
connects
a
to my
pure
question.
condensate will give you, this is how you know you have a pure condensate dark
and
matter.
what would happen if you would have, let's say sterile neutrinos, and they would be distributed in a certain density in our galaxy? Could you also describe, would this fall? Of course, you can't describe neutrinos via a Bose-Einstein condensate, but you can still describe the density profile, probably to a certain extent by that. So if you're only after the density profile, so my question is, could you detect also, if it were neutrinos, let's say sterile neutrinos, could you see them in in similar schemes as you are?
So all there is you have 2 detectors and you look at correlations, like time delay correlations between them. And what I'm trying to think, and I'm a bit hesitant about, is what does the time delay correlations for sterile neutrinos tell you? Definitely it'll give you some information about the local density profile. How much of it is related to its astrophysical properties, that's where I'm putting a stop. So for this specific case, I know I can relate it to another galaxy merged into mine, but I don't know if I can say stuff like that. We should talk,
That's last question. You need more. Okay, I have a naive question about the photon and dark matter cloud, for example. If photon moves inside this cloud, if it's interact with dark matter, should I expect speed of light will change because of refraction index and so on? Because you have interaction as in matter, usually. Speed of light.
I think there are limits to that from the bullet cluster merger and stuff. So I think those effects have been, or that chain of thought have been used to set bounds on the dark matter cross section. So somebody has thought about it. There are some numbers out there. I don't remember the number, but
it means that speed of light not a constant,
Why?
Speed of light, is not a constant.
No, it will be. Yeah. Okay. Okay. Yeah. All right. Yeah.
Okay. Well, if there's no other questions, let's thank Swati and all the speakers.